Can you see my screen? No, something is not working. Let me rejoin the meeting. So wait, my this file is not working. So just wait. I'll rejoin the meeting.
Okay, sir.
So can you see the screen?
Yes, sir.
Okay, so let us see what are the procedure that we have to adopt in order to calculate the triple integral in spherical coordinate. So let's say I want to calculate this triple integral in this spherical coordinate. So first step is again similar to what we have done before. Sketch the region of integration and its projection. Let us denote this projection by R in the XY plane. Then second step, draw a ray from the origin which makes angle phi with the positive z axis, and its projection, that is projection of the ray M. Let us denote the projection of the ray M by L on the XY plane. Okay. So you imagine you have three-dimensional space and you imagine a point in three-dimensional space. You draw a line from the origin to this point. This will give you, from there you can identify the angle that this line from the origin to the point, to that particular point. What is this? Identify the angle. Okay. Then you identify the projection of this line to the xy plane. Okay, and then identify the angle that this projection makes with the x-axis, positive x-axis. Okay, so projection L makes an angle theta with the positive x-axis. The ray makes an angle phi with the positive z-axis. Then identify the points where this ray M enters the region, and let us assume that the ray M enters the region when rho is equal to G1 R theta, and exit the region D when rho is equal to G2 R theta. This gives you the limit of rho, which is from G1 R theta to G2 R theta. Okay, so you may remember that we have three components in the spherical coordinate. So for all the three components, we have to identify the range. So first we have identified the range of rho in this step. Then you fix a value of theta. So remember that theta is the angle that the projection of the ray M to the xy plane makes with the positive x-axis. So for a given theta, phi limits will be from phi 1 to phi 2. So identify, if you fix value of theta, so at this value of theta, you identify the range of phi by moving the ray from the angle, so that uh, moving the ray along the z-axis, so that this makes uh, angle phi 1. It will exit the region at angle phi 1, and that gives you the lower limit of phi, and exit the region at angle phi 2, that gives you the upper limit of phi. And then in the projection, identify the range of theta in the usual way. Okay, so these are the steps that we have to follow. So let us consider this example. Find the volume of the solid D. Find the volume of the solid D bounded below by a cone phi is equal to pi by 3. So first of all, we plot a cone at phi by 3. So you can see that we have this cone at angle phi by 3. This is the cone in the picture at angle phi by 3. So you plot the cone, and then the region is bounded above by the sphere rho is less than equal to 1. So this is the sphere with rho less than equal to 1. So boundary region is given in this picture 52. All right. So this is the first step. First step was to plot the region D, and then you have to also plot the projection of the region D in the xy plane. So let us project this solid shape in the xy plane. The projection is a circle, which is given here in this picture. This is the projection of this solid in the xy plane. Okay. So the first step is done. Now we have to go to the second step. In second step, what we have to do, we have to draw a ray from the origin which makes angle phi with the positive z-axis, and we also draw the projection of this ray, which we denote by L, to the xy plane. Okay, so let us draw a ray. So first of all, where is this origin? This is 0 here, and this is 0, and this is also 0. Okay, so that means my origin is this point somewhere here in the projected region xy plane. Now you draw a ray which will make angle phi with the z-axis. So let us say this is z-axis and this is angle phi that this ray makes with the z-axis. And you also put the projection of this ray in the xy plane. So let us say that the projection is this. Okay, this is the projection. Projection makes angle theta with the positive x-axis. So here I think due to symmetry you can take any axis as z-axis. So let us say this is z-axis. So this is angle theta. This was angle phi. Fine. So we are able to do the second step. We have plotted a ray from the origin making angle phi with the positive z-axis and its projection L to the on the xy plane. The projection makes an angle theta with the positive x-axis. Now identify the range of rho. How do we identify the range of rho? We see the entry point of this ray M inside the region D and the exit point. So entry point of this ray M inside the region D is this one. Rho is equal to 0. This is the entry point. And the exit point, this was the ray M. And exit point is on the sphere. Right, so this is the exit point, so that means rho is equal to 1. On this sphere, the value of rho is 1. So that means the integral is from 0 to 1. Okay. Now you are able to identify the range of rho. So now you identify the range of the other variable. So what you do is you fix a value of theta. So let us say if this theta is fixed in the xy plane, then this ray is also fixed. So that means so rotate this ray in different directions on the left hand side by fixing the value of theta, and also to the right hand side, and see where this this ray will exit the region and where this ray. So identify the points where this ray will exit the region. So this ray will exit the region when you go to this point. Okay, and to this point. No, sorry, just a second. For a given theta, because this is an angle with the positive x-axis, so basically you identify the value of phi. Yeah, so with the positive z-axis, only with this positive. So basically you start this ray from this point, from this z axis, the angle is 0, and then you rotate this ray to this side, the angle with the positive z axis is pi by 3, and from here it will exit the region. Okay, so only the half circle you make. So the limit of rho phi will be 0 to pi by 3, and then you rotate the value of theta in the projected region. So projected region is this circle. This is R, the projected region. So if I rotate the value of theta in the circle, the value of theta, the range of theta will be from 0 to 2 pi, because projection is circle. So the range of theta is from 0 to 2 pi. So you get this range. Okay. So the required volume is triple integral over the domain D of the, this is the infinitesimal volume, and this we have seen in our last lecture. The infinitesimal volume is this quantity. This was the proof here. So when delta rho, delta phi, and delta theta goes to 0, this basically becomes rho square sine phi d rho d phi d theta. Okay. So this is this is how you obtain the range.
Sir?
Yes.
Sir, if in the question it is written that cone phi equal to pi by 3, it means that the apex angle equals to pi by 3, right?
Yeah, this angle is with the positive z axis. So you have, let's say.
So when we take phi
Sorry,
apex
say again.
angle,
When we take.
when we take phi, the limits of phi, it should be from 0 to pi by 6, right? Because it is, we are taking the half of the apex angle as the upper limit.
No, 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 no. So how do you draw the cone? This is z axis. This is my z axis, and with the z axis it makes angle pi by 3. So cone is located at this point. So you have this. Oops. You have this cone. So it is making angle this. So this is my cone. It is making angle pi by 3 with the positive side of the z axis.
Okay, yes, sir. Okay.
Do you follow this?
Yes, sir. Yes.
Yeah. Because if you put a ray here with, if you put a ray here, if you put a ray at angle pi by 3 from the positive, which is made with the positive side of the z axis, and rotate this ray around this entire circle, uh, right, around the z axis, you will get the cone.
Yes, sir. Yes.
Okay. So this is that is. Okay, and then rest of the integrals are easy to evaluate, so you can, so these are all simple integrals, you can do this. Now conversion from the rectangular coordinate to the spherical coordinate, it is pretty much straightforward. The points in the rectangular coordinates are denoted by x, y, and z. So we substitute x is equal to rho sine phi cos theta, y is equal to rho sine phi sine theta, and z is equal to rho cos phi. So do you know how this conversion is made, or should I explain?
No, sir, we know.
You don't know?
No,
So
sir, I know.
let's
Sir, we
say
know.
Okay, anyway, I will explain very quickly. So let's say we have this x-axis, and this is y-axis, and this is z-axis. And let us assume that I have a point x, y, z in this three-dimensional space. So this is my origin, this black point. So from the black point, I start a ray. Okay, and I say that this ray will make an angle phi with positive z-axis. Okay, and then you project this ray in the xy. So projection is like this line. Projection of this ray, which is making angle phi with the z-axis, is this line, and let us assume that this makes an angle theta with the positive x-axis. Okay. So now you have you can easily calculate these lengths. So what is the length of this quantity?
R sin phi.
Yeah. So if this is rho, not r, this is, let's say, the length of the distance between the origin and the point x, y, z is rho, then this angle will be rho sine phi. Okay, because this is your right angle triangle. Okay, and then once you have this the length of this projection, then you can find the length of the x component by multiplying this by cos theta, and length of this y, you can obtain the length of y by multiplying this by sin theta. So you get rho sin phi and sin theta. That gives you y. So that is why you see that you have y as this quantity and x as this quantity. And how you calculate the length of z? Length of z you calculate by projecting this ray on the z-axis. So that is your z. So again you have this right angle triangle. So base of this will be rho times cos phi. So z is rho times cos phi. Is it okay?
Yes, sir.
Yeah. So this is how you calculate. Now with this transformation, we can write the integral in the rectangular coordinate. We can transform this integral in the rectangular coordinate to the spherical coordinate. So simply substitute the value of x, value of y, and the value of z. And the volume, this was the volume in the rectangular coordinate, right? Infinitesimal volume in the rectangular coordinate. Right? So this we have to replace by the volume in the spherical coordinate. And the volume in the spherical coordinate is this one. This is the volume in the spherical coordinate. Okay. So this is how you transform. Is it fine?
Yes, sir.
Yes, sir.
So now we solve one exercise on this. So consider this example. Consider this example. we want to evaluate the triple integral of this quantity over the region D, where D is the volume of x square by a square plus y square by b square plus z square by c square is equal to 1. So what we do is we substitute x by a is equal to u, y by b is equal to v, and z by c is equal to w. So from this three relationship, what we get is dx is equal to au. From the second one, we get dy is equal to b dv, and from the third one, we get dz is equal to c dw. So which means dx, dy, dz, which is the volume in the spherical in the volume in the rectangular coordinate, is basically a b c du dv dw. So from one spherical rectangular coordinate, we are moving to another rectangular coordinate. First was with this one the first one was x y z. Now you have u v w. Okay, fine. So this triple integral is basically equal to, we substitute this value. So x by a is u, you put it here. Y by b is v, you put it here, and z by c is w. So you get triple integral of 1 minus u square minus v, 1 minus u square minus v square minus w square, and dx dy dz is basically that we have just calculated, abc into du dv dw, and abc can be taken out of the integral because these are constants. So you have this triple integral, and where d is replaced by now d star. But what is d star? D star is just this sphere with this in the new transformation. So my d was x square by a square plus y square by b square plus z square by c square is equal to 1. Now my d star is u square plus v square plus w square is equal to 1. Okay, so this is what we have, is d star here. And so we have this volume of u square plus v square plus w square is equal to 1. Now further on converting to the spherical coordinates, so now we make this transformation. So we make u is equal to rho sine phi into cos theta, v is equal to rho sine phi into sine theta, and w is equal to rho cos phi. By this substitution, we put the value of u, v, and w here in this integral. So what do you get? You get 1 minus u square plus v square minus w square, and 1 minus u square minus w square is this quantity. In fact, this quantity, I will say, after this substitution, u square minus v square minus w square is minus rho square. Okay, so you get 1 minus rho square, and this is the volume in the rectangular coordinate. So we have to replace this by the volume in the spherical coordinate. Okay, which is in spherical coordinate, the volume is this one. So this will come here in this calculation. So you get 1 minus rho square times the volume here in this spherical coordinate. Okay, now the everything else is the integral is over the sphere d star, whose equation is u square plus v square plus w square is equal to 1. This is the equation. So now you imagine a sphere in the three-dimensional space, and start a ray from the origin, making angle phi with the z-axis. This ray enters the region when rho is equal to 0, and it will exit the region when rho is equal to 1. Okay, so the limit of rho is identified. Now you see what are the angles that this ray will make with the z-axis, the positive side of the z-axis. So since you have the entire sphere, so if I start a ray from the xy plane and rotate it by uh, 2 pi, start a ray from the z-axis, because the angle is with the positive side of the z-axis. So the ray is exactly on the z-axis, and then you rotate this uh, at a fixed angle theta of in its projection. So this will make an angle 0 to 2 pi. I do not have too many pictures to explain. So you have this sphere, right? And let us say this is your z-axis. So you start a ray from z is equal to 0 and then rotate this. So when you rotate this, to cover the entire sphere, you have to come up to this point, given the value of theta is fixed. Okay, so that means the range of so range of phi will be 0 to pi, because this full rotation from here to here is 0 to pi. And then the projection of this sphere in the xy plane will be a circle of radius 1. So to cover the entire circle, the value of theta will vary from 0 to 2 pi. So you have this range. Okay. Fine. Okay, so now you can evaluate this integral one by one. First, with respect to so there is a typing mistake. This should be d rho. So first, with respect to rho, keeping theta and phi constant, then the second integral you can evaluate with respect to theta. Here the theta and phi do not depend on each other, so you can change the order also using the Fogni theorem in 2 dimensions for in R2. Okay, so then with respect to theta and then with respect to phi. So this integral is evaluated here. Explicitly, the value comes out to be this. So you can see this calculation. You can verify this calculation at home. Any question here so far? Any question? So no questions. Then we move to this next topic, which is Jacobian transformation. So first of all, I'll revisit the Jacobian transformation in one variable. Let us say that I want to integrate this function f over the interval a to b. Okay, and I substitute x is equal to g of u. Fine. So
Yes, sir.
also assume that g is differentiable and it is either increasing or decreasing. Fine. So that means if function is increasing or decreasing, that means the function is in is one to one, or it is invertible. All right. So we can solve this because function is invertible. So we can solve this by saying that u is equal to, let's say, the inverse of g x. Now when x is equal to a, u is equal to g inverse a, and when x is equal to b, u is equal to g inverse b. Fine. So you have this limit. If it is increasing, the g inverse a will be smaller because a is smaller, and similarly g inverse b will be bigger because b is bigger. So the range will be from g inverse a to g inverse b. And then you write x as by using this relationship x is equal to g of u. So replace x by g of u, and this dx will be replaced by the derivative of g with respect to u, this quantity times du. So this quantity that you see, this additional thing that you see in this expression, this is known as Jacobian in one variable. Okay. If the function g is decreasing, so this is the case when the function g is increasing, and now if the function g is decreasing, if the function g is decreasing, then you just interchange the role of this this limit. So you have g inverse b will be less than g inverse a, and you put a minus sign here, and this you can write as modulus of this quantity. So this becomes the Jacobian in this case. Okay. So regardless of whether g is decreasing or increasing, the integral of f over the range a to b is equal to integral of this quantity over the range c to d. Okay, so this is known as Jacobian. Now let us translate this to two-dimensional case for function of two variable, and then we will see another theorem for function of three variable. So for this, let T be one-to-one transformation from the region R tilde in UV plane. So you have, let's say, one region. You have this UV plane. This is UV plane, and let us say that this region is there in the UV plane, and this region is R tilde. Okay, to the plane. So this transformation is to we plot this one-to-one transformation from the region R tilde to the region R in the XY plane. So let us say we have this XY plane. This is x-axis, this is y-axis. Let's say in XY plane we have this region. So by transformation T, we plot the region R tilde. We transform the region R tilde in the UV plane to the region R in the XY plane. Okay.
Yes, sir.
Sir, why are we taking modulus?
Modulus, so that we have explained here in this one dimensional case. It can be increasing or decreasing. So in any case, if you put the modulus, you get the same thing.
Yes, sir.
Is it clear?
Sir, but if we don't put the modulus, then sign will be opposite.
No, what sign is opposite?
Sir, suppose
So
it is negative.
basically, by putting the modulus, we really do not care whether the transformation is increasing or decreasing.
Oh, okay, sir.
Okay, we don't care. Otherwise, if you start caring about the increasing and decreasing transformation, then you have to, if it is increasing, then you use this one. If it is decreasing, then you use this one. So these two cases are combined together to arrive at this expression. Right?
Okay, sir.
Right. So then the double integral over the region R of f is equal to double integral over the region R tilde of f, and here x is transformed. We make this transformation, x is equal to g of uv and y is equal to h of uv. So replace x by g of uv and y by h of uv. And after this replacement, you multiply this by the Jacobian transformation. Okay, where Jacobian transformation is given by the first row of this Jacobian transformation. So when you, this is the right notation for Jacobian transformation. So this is the Jacobian transformation when you come from the UV plane to the XY plane. When you do this transformation from the UV plane to the XY plane. That means the integrals are given in the form dx dy or dy dx, and you want to make this transformation by putting x is equal to g of uv and y is equal to h of uv, then this is the Jacobian. And this Jacobian is constructed, whatever you write in the numerator, so numerator you have xy and denominator you have uv. So from the numerator you pick one variable x and differentiate this with respect to these two variables. That will give you the first row. So x is differentiated with respect to u and x is differentiated with respect to v. Then you pick the second variable in the numerator and differentiate this with both the variable in the denominator. So that gives you the second row. Derivative of y with respect to u and derivative of y with respect to v. All right. Proof is not required, but at intuitive level you can understand this transformation. And this is well explained in the example. I'll go to this example. This is three-dimensional. I will go to this example first, and then I'll return back so that you know what is going on at intuitive level. So we have to find the mass of the plane bounded by parabola y square is equal to 4ax. Y square is equal to 4bx. You have two parabolas, y square is equal to 4ax and y square is equal to 4bx. Okay, so let's say this is y square is equal to 4bx, and this green line is the parabola y square is equal to 4ax. Then you have another two parabola, x square is equal to 4cy. So let's say this is x square is equal to 4cy, and then the blue line is x square is equal to the last one, 4dy. And the region bounded by these four parabolas is this region. Okay, fine. Now it asks you to find the density at point the density at point xy in this region. We have this, let's say, point xy. So at this point the density is fxy, which is given by k times xy. Okay, and then you have to find the mass, right? So mass formula we have already seen. What was the mass formula? Mass formula was double integral over the region R of
MDM.
sorry, right?
Yes, sir.
This was the formula for mass. Now we have to find this integral. The region of integration is R, which is this region, and we want to find this integral. So basically you can substitute the value of f also. So this is k times xy dA. So by making a transformation to another plane, you have to find this integral. So first of all, let us see what transformation we have to make. Let us assume that u is equal to x squared over y and v is equal to y squared over x. So if I take u is equal to so this first parabola will become, by using this transformation, y squared over x is v. So v is equal to 4a. Second parabola will become v is equal to 4b, right? Third parabola is x squared is equal to 4c. So you bring y to the left hand side, you have x squared over y, and x squared over y is u. So u is equal to 4c. And x squared is equal to 4d, which means x squared over y. So you get u is equal to 4d. So now you see we had 4 parabolas in the xy plane. Now these parabolas, if I plot in the UV plane, they will look like straight lines, right? They are basically straight lines. One straight line at u is equal to 4c. So let's say this is u is equal to 4c. Another straight line u is equal to 4d. So this is u is equal to 4d. Another one is v is equal to 4a. So you can say this is v is equal to, just but arbitrarily choose v is equal to 4a. This is another straight line, and this is another straight line. V is equal to 4b. Now you see what a wonderful technique we have here. We wanted to work on a complicated region. Our original task was to find the double integral on a complicated region. Now don't say that this is not complicated. Complicated is also a relative term, but when I say complicated, means you need to work a little bit more as compared to this rectangle. So this shaded region that is by this transformation is transformed to a rectangle. Right? This shape. This was the shape we have in the xy plane. So this shape by this transformation becomes a rectangle. What is going on? Fine. So working integrating over a rectangle, which one is easier? Integrating over this region or integrating over a rectangle? Which one is easier? Obviously, the integrating over rectangle is easier. But then you have to be careful when you make this transformation. You cannot simply transform this. You cannot simply replace this double integral over this complicated region by the double integral over this rectangle. You have to compensate for that. And what is that compensation that you have to make? That compensation is the Jacobian. ठीक है? Because if you take an infinitesimal area here, this infinitesimal area, these two should match. Okay? So to make them match, you have to multiply by certain quantity. ताकि तुम, you can from here you can go to this one, and then from here you can come to this one. Right, so that quantity is Jacobian. So if I use this formula of Jacobian that we have just seen now, so we can find the Jacobian of this transformation. So basically this is xy del xy del uv. So as I said, you differentiate x with respect to the variable u and v, you get the first row, differentiate with the variable y with respect to u, v, you get the second row. So x derivative of x with respect to u, you have this transformation. So first of all, solve this for x. You have two variables x and y, and two equations, u is equal to x square over y and v is equal to y square over x. So you can obtain the value of x and y in terms of u and v. So when you solve these two equations, you get x is equal to u raised to 2 by 3 and v raised to 1 by 3. And y is equal to 1 by u raised to 1 by 3 and v is raised to 2 by 3. Now you can differentiate these quantities. So derivative of x with respect to u, derivative of x with respect to v, these are the derivatives. And derivative of y with respect to u is this one. Derivative of y with respect to v is this one. And this is determinant of this quantity. So you can solve this determinant, which will come out to be 1 by 3. Is it fine? Okay, so that means my Jacobian is 1 by 3. So what does this mean? This means that, oh, where is it gone? Now, if you look at this picture, which area is bigger? The area given in picture 54 is bigger than the area given in picture 53, right? So that means in order to match the area, when you transform this integral, you have to multiply this area by 1 by 3. So that when you multiply this by 1 by 3, ultimately you come to this area. And this is what the Jacobian does. In this case, the Jacobian came out to be just a constant. So a simple multiplication by a constant will give you the same area that you have of the rectangle. You multiply the area of this rectangle by 1 by 3, which is Jacobian. Then the area comes out to be exactly this area. Okay. So this is the purpose of the Jacobian. Now the area in this case comes out to be 1 by 3. It is not necessary that you will get the area constant in all the cases. It may also depends on the point UV in the UV plane. Okay. So you get this as Jacobian, and then you can simply translate this integral. The integral was over the region R, which was given in the first picture. Now the integral is over the region R tilde, which is given in the second picture, which is rectangle. And my transformation is x is equal to, so substitute this value of x, and y is this one, substitute the value of y, and now this dy dx will become Jacobian times du dv. Integral is over r tilde. Now r tilde is a rectangle, so you can easily calculate the limits of x and y. Limit of x is from here to here, limit of y is from here to here. Okay, so here this limit is for v, limit of v is, sorry, v and u and v. So limit of v is 4b to 4c, limit of u is 4d to 4, limit of v is 4b to 4a, limit of u is 4d to 4c. And when you solve this integral, ultimately you will get this value. Is it okay?
Yes, sir.
Is it fine? Are you following this?
Yes, sir.
Yes, sir.
Okay, so mathematically we have not proved the result for the Jacobian transformation, but you know at least at the intuitive level what does this Jacobian when we transform from the UV plane to the XY plane. Okay. Now look at this example. Let us go back. So this is another example of the Jacobian transformation. So remember that if you recall from our previous discussion on double integral, in double integral, this was the infinitesimal area, dx dy was the infinitesimal area in the rectangular coordinate. And when we transform this to, when we transform this to the rectangular polar coordinate, then this is the area in the polar coordinate. Okay, but you see that this
I think we should start. I don't know. The number of students is around 50 only. So shall I start or shall I wait for a few minutes?
My back! Oh, my back!
So you can start. It's 4-5.
Okay, Shruti, I think we will start. You are right. Can you see the slides?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. Today we are starting a new unit that is solid state chemistry. You would have studied a little bit of solid state chemistry, I hope.
Yes.
Yes, sir.
Yeah. And here the topics we will be covering. I am supposed to take 5 lectures. Then we are going to get only 4 lectures, but I will see how it goes. If required, all of you agree, I will arrange one more lecture depending upon the convenience. Okay. The different topics we will be covering is bonding in solids, diffraction methods, primarily X-ray diffraction. Under this diffraction methods, we will talk about scattering of X-rays from a crystal. What is the basic principle? And there is something called structure factor. And the structure factor actually determines what is going to be the intensity of a particular reflection, for example, in X-ray diffraction. And there is something called systematic absence. Have you heard this word before? Systematic absence? Probably no. Huh?
No, sir.
Systematic absence? No. Okay. I will anyway. This one I will teach you in the next class. But today I will just introduce to you. Systematic absence means some particular lattice. You may have absence of a particular reflection. That particular. Okay. So I hope you can hear me now.
Yes, sir.
Yes, sir.
Okay. So the synthesis of solids, we will talk about. There are actually many methods of synthesis of solids. We will mainly talk about ceramic method. What do you mean by ceramic? Anybody know what is meant by ceramic? I say that aluminum oxide is a ceramic material. Why it is called a ceramic material?
Neither metallic nor organic.
Neither metallic nor organic. Then what about a semiconductor? Suppose let me say cadmium sulfide. Cadmium sulfide is not a metal. It is not organic. But can I call it as a ceramic? Cadmium sulfide? The answer is no. Actually, ceramic material is usually the materials used for high temperature applications. Anyway, in this case, the synthesis of solid by ceramic method means you will use really high temperature to make solids. And there is another method called salt gel method. So this is basically a solution-based method. As the name suggests, you will have some kind of sol, which is a colloid. Then the colloid will become a gel. We will talk about it later in depth. Hydrothermal method. This method is basically using water as a solvent, and then you will have some temperature and pressure to make some special solids. That is why we call it as hydrothermal method. And the two other methods we will talk about is a microwave method and sonochemical method. All of you know what is sono means? Sono, S-O-N-O means what?
Yes.
Related
Sound.
to something sound.
It is related to sound, you are right. Can you use sound to make chemistry? That is the question. The answer is yes. You can use not exactly because of the vibration you produce sonic waves. That waves are used for making solids. So that is why it is called sonochemical reaction, so also no chemical synthesis. Now let us talk to why people are interested in, because anything we study, there has to be some motivation. Most of the materials we use for applications, starting from electronics, storage of data, many applications, you will see that solids have a big role to play. And many compounds exist as solids under suitable temperature and pressure conditions. And some compounds will exist only as solids. And solids have a lot of technological importance. So one has to know its structure, its property, how to make it, what will happen if I make it into different shape, what will happen if I reduce the size of the particle. I need to understand everything. So studies on solid is very, very important. I have put one slide just to provoke some interest of solid-state chemistry. You see that application, it is so diverse, starting from gemstones, and you are ending in sensors. These are some of the important applications of solids. You can use it as an abrasive material. You can use a lubricant, for example, graphite. Molybdenum disulfide is a lubricant. The semiconductor in the entire electronics industry is based on semiconductors. So silicon and germanium, for example. There is something called superconductors. By the way, where the superconductors are used?
Car batteries.
Any other answer?
Sir, in the circuits.
In the circuit. You mean superconductor?
Yes, sir.
By the way, what is a
fusion
superconductor?
reactors.
Magnetic levitation.
Who said magnetic levitation? I think Utkars?
No, sir. Me, sir.
Okay. It's a very interesting, you people came up with different answer. Superconductor is a one which has zero resistance below a particular temperature called critical temperature. We call it as TC. Now, if your material is superconducting, that means it has no resistance to current. So you can push so much current. Now the question is, where you use superconductors? It is used, for example, wherever you want a very high magnetic field application. You want to generate huge magnetic field using an electromagnet, then obviously you have to provide a lot of current to the coil. Now the question is, the coil you are making, that will have some definite resistance. If that coil is made out of superconductor, you can push so much of current and you can generate a very high magnetic field strength. Now where it is used? It is used in, for example, nuclear magnetic resonance spectroscopy, magnetic resonance imaging, and magnetic levitation, for example. That is a concept used for superfast trains. Anyway, superconductor is a very interesting subject. So I have just given that, interesting solids. You see the difference here between two solids I have given. One is on metal oxide, actually, yttrium, barium, copper oxide. The another one, it is NB3SN. It is an alloy. So you find superconducting property not only in an alloy, you also find it in a metal oxide. Very, very interesting. Electrolyte. Most of the batteries, you need electrolyte. So the electrolyte can be solid. Lithium iodide, for example, is an electrolyte. Piezoelectric material, quartz. Magnetic recording, mainly metal oxides, you can see. Iron oxide, chromium oxide. Phosphor material, mainly used for luminescence-based application. And lasers. Now the question is, where laser is used?
You know how much I sacrificed?
Okay, where laser is used?
Sir, in the N photons reaction, sir.
Okay.
In our
use
femtochemistry.
Yes, very good. I think we're coming up with a very good answer. It is used in, for example, spectroscopy. If you want to probe a process at a very, very low time scale, picoseconds or femtoseconds, you use lasers, for example. If you want to probe mechanism of a reaction of that time scale. It can be used for surgery. It can be used for missile defense. So many applications, lasers. Obviously, you need a solid to generate a laser. And the catalysis, whatever we talked about in the previous unit, many of them are solids. You can see zeolite is the catalyst. And there are many sensors, for example, zirconium oxide. So the motivation behind studying solid state chemistry is that there are so many applications one can think of. And in principle, in the periodic table, you have so many combinations possible, there are so many solids, and it is very, very diverse field. The first topic in the solid state chemistry is given is bonding in solids. Now, all of you know the material, you can have different types of forces which are holding together these atoms or molecules or ions in a solid. So, obviously, the attractive and repulsive forces will be acting on the atoms and molecules, and then you will have a equilibrium position. Then only it becomes a solid, for example. In principle, or you can say primarily, there are at least 4 different types of forces which are found to be in solids. One is the van der Waals forces. Another one is covalent forces or covalent bonding you will have. And another one is ionic bonding and metallic bonding. Now, I will give you some example of each one of this. For example, if you take iodine solid, I2, what type of bonding is there in I2? Do you have any idea? Is it covalent bonding?
Ionic bonding.
I2 solid I am talking about.
Covalent.
It touches in I3 minus and I think it's ionic bond.
Okay. Don't confuse with I3. Van der Waals is a correct answer. Remember, I3 minus will form when I2 reacts with I minus in water. Then you will get I3 minus. Here we are talking about solid I2 we buy from any commercial supplier, which will look like a purple color solid. And then all of you know that it sublimes very easily. Okay. In fact, iodine is an example. We call it as molecular solid. The bonding is actually very, very weak, van der Waals forces. And van der Waals forces are basically long-range interaction. Covalent forces are much stronger. For example, I can give straight away an example. If you take SiO2, quartz is kind of a covalent network solid. Ionic bonding, obviously you would have studied a lot of things about ionic solids, sodium chloride, magnesium oxide, calcium oxide. There are many ionic solids, and obviously you have Coulombic forces acting here. And the last one, metallic bonding. Now in metallic bonding, actually you will have CF electrons, and basically you will have kind of interaction between the CF electrons and positive nuclei. Now, van der Waals forces act upon, if you have the solid which is constituted by molecules which have permanent dipole moment, they can have interaction between them, and then you have a long range interaction which has a R power 6 dependence. The attractive interaction has R power 6 dependence. Okay. And even if you don't have a permanent dipole in your molecule, you can still have some induced dipole moment because you have some neighboring molecules. So you can have induced dipole moment. Again, that can be also leading to this kind of interaction, leading to formation of your solid. So iodine is an example of this van der Waals forces solid, and this is also called molecular solid. If you take iodine, it has very, very low melting point actually, because the forces are not very strong. On the other hand, if you take sodium chloride is ionic solid, and you'll find the melting point, all of you know, it's very, very high. Okay, I think. Now, covalent forces, basically you have the atoms are covalently linked with each other, and the bonding extends throughout the lattice. Now I have to ask one question here. Does anybody know what is meant by lattice?
Yes, sir. The structure, molecular structure.
It is a spatial arrangement of an atom.
Very good. Spatial. Then what is the difference between a unit cell and a lattice?
So lattice is made up of units.
Lattice is a collection of unit cells.
Okay, I will straight away go to that slide. Okay, so that the concept is very clear. All of you are familiar with this, but still I will show that so that it is very clear to you what is a lattice. And okay, this slide I think will nicely explain what is a lattice. I hope you can see the slide, correct?
Yes.
Yes, sir.
Lattice is an array of points in space. I will repeat. Lattice is an array of points in space. It can be a three-dimensional array, for example. In this, each red dot is actually a lattice point. Now, the lattice can be generated using some kind of basis, we call it as. For example, you can have a rectangular unit cell, a square unit cell, and so forth. A lattice is generated using a basic unit. We call it as a motif. In this case, they have drawn a fish. That is actually just for understanding only. You see that each lattice point is occupied by a motif here. Now, if you look at the right side, the motif is not sitting on the lattice point. I will repeat. If you look at the right side of the bottom, you will see that the motif is not sitting exactly on the lattice point. What does it mean? Lattice point is kind of an array of points in space, and your motif need not be exactly sitting on the lattice point. You can still generate a lattice if it has a displacement, for example. Okay. So lattice, the answer to the question lattice means you are talking about array of points in space. And remember, lattice point is not a physical object. It need not be a physical object. You can place a physical object on a lattice point. Okay, let me now come back to because I introduced what is lattice.
Motif was?
I'm sorry, Steve, again, tell me.
Can you tell what motif is?
Motif is the basic unit. For example, it can be a group of atoms which I use to generate the structure. Okay. Motif means the fundamental building unit. You are going to use it to generate a structure. Without that, you cannot generate a structure.
So is it like unit cell?
Okay, I will. Unit cell is again, now the question is, what is the difference between a unit cell? Here you can see the left side, okay? What is a unit cell? Whatever is drawn in the line, for example, look at the top left. Something is written in P, and then you have 4 points in the corner. This is actually the unit cell. Okay? Unit cell is made out of motif. You see that there is something written here, P. Does anybody know what is meant by P?
Planar?
Good guess, but that is wrong.
Parallelogram. Primitive unit.
Very good. Primitive. And NP stands for non-primitive. Okay. Does anybody know what is the difference between these two?
There?
Sir, in primitive, the lattice points will be at the corners, and in non-primitive, there along with the corners, there will also be at some other places.
Excellent, Karthik. Non-primitive means you are having, in addition to the corners of the unit cell, you also have some lattice point, for example, in the middle of the face, for example. NP stands for non-primitive. You take this unit cell, you see that not only it has corner lattice point, but also in the middle. Anyway, when I talk about X-ray diffraction, we will see little more in depth. Whatever question you have, you can ask there. Right now, we are talking about bonding, and then I was trying to explain what is lattice, so I jumped there. Let us get back to where we were. We were talking about van der Waals solid, then we were talking about covalent solid. And covalent solid, we were giving some example. You see here, graphite, diamond, quartz. I have taken some interesting example here. Is there any difference between graphite and diamond?
Yes, a structural difference.
Structural differences.
Both are covalent solids only, but structurally there is some minor differences there. Do you know what is the difference? I am sure you know.
But there is hexagonal.
Graphites are like hexagonal.
Graphite has layer kind of structure.
Diamond
has a network structure.
Is like
Hexagonal.
Okay. If somebody asks you the fundamental difference between graphite and diamond, you say that one is layered structure, another one is not layered structure. Diamond has no layered structure. It is more close packed structure, and graphite has a layered structure. And that is the reason actually graphite is a lubricant and diamond is not a lubricant. Graphite is used as a solid lubricant because it has layered structure and these layers can slide when you apply pressure. So really graphite is a very good example, but it is an example of covalent network solid. These materials are very hard, but graphite is not that very hard. Diamond is really hard. In fact, diamond is used to cut glass. It's very, very hard. And they are also refractory. Now the question is, what is meant by refractory?
Sir, high boiling point.
High boiling point. Okay.
Sir, refractive index is high.
Oh, okay. Don't get confused between refractory material and refractive index. A material with high refractive index is not called a refractory material. It has no relevance. Refractory is a different terminology. It stands for resistance to heat. If some material has resistance to heating, basically most of the ceramic materials we call it as refractory material. Okay. All of you knows furnace. Have you heard about furnace?
Yes.
Yes.
For example, I want to heat my material at 1000 degrees Celsius. I use a furnace. So in furnace, what is the fundamental principle of a furnace? Basically, you will have, for example, it is based on Ohm's heating only. You will have a ceramic material in which you will have a coil wound on it, and then you will pass a lot of current through it, and then the power dissipation will increase the temperature of the furnace. And you can control the power, obviously you can control the temperature. So you need high temperature materials to be used in furnace. And those materials are actually refractory materials. You will see that they don't yield to the heat treatment. Nothing will happen to it. Of course, not every material you can use it as a refractory material. I can give you an example. Aluminum oxide is a very good refractory material. Silicon carbide is a very good refractory material. There is a commercial name for silicon carbide. Does anybody know?
Carborundum.
Carborundum. Okay, there is a company called Carborundum Universal, which makes silicon carbide and sell it. So it is a refractory material. It is a refractory material. Of course, silicon carbide has a covalent framework solid actually. Now, ionic solids, there are so many examples. So basically, the solids consist of positive and negative ions and held together by electrostatic forces. And each ion will be surrounded by the oppositely charged ions, and you will have the second neighbor actually. That will be the similar what you started with, so that the original ion on the second layer will start repelling. So all of you are familiar with this, like, ionic solids. And then this concept is used in ionic solids, lattice energy of crystal. Basically, it is the amount of energy liberated when you have 1 mole of infinitely separated ions are brought together to form 1 mole of solid. So I think basically it is an electrostatic interaction between the ions in an ionic solid. And sometimes people use this equation to calculate the lattice energy for an ionic crystal. I am not going to ask any numerical problem and all, just I wanted to give you this. UL is a lattice energy which depends on the number of molecules, and you have capital M, which is called a Madelung constant, and Z1 and Z2 are the charges of the ions, and E is the electronic charge, and this R0 is the equilibrium distance between the cation and the anion in your ionic crystal. And then you have a factor called N, It is called Born exponent. Probably you have studied this, but I just gave you this just to in the context of ionic crystals. Now, anyway, I think I explained to this. Metals have something very unique property. High electrical conductivity and high thermal conductivity. And now the question is, how do you explain these behaviors? Like, what type of bonding we have? I was telling you, in a metal, you have a sea of electrons. That means you have highly kind of delocalized situation. These electrons are there. Now, how you are going to explain their behavior? All of you are familiar with most of the metals conduct very good electrical conductivity. Which is the best metal in terms of electrical conductivity?
Silver.
Silver. Okay, very good. By the way, I will tell you something. Mercury. Mercury is an interesting example. It is, of course, all of you know it is metallic and it's a liquid, but mercury can become superconducting at a very, very low temperature. Okay, this is an interesting observation. But then in the history of superconductivity, people started looking for other materials, and then they came up with a lot of materials whose critical temperature is very, very high compared to that of mercury. Mercury becomes superconducting at very, very low temperatures, like liquid helium temperatures, close to 4 Kelvin. Now, there is something called band we all the time talk about. I'm sure you have come across this band terminology somewhere. Is that correct?
Yes, sir.
Semiconductor.
In semiconductor physics.
Band and valence band.
Yes, sir.
Yes. Valency band and conduction band you would have studied. And you would have also studied that a metal doesn't have a band gap. A semiconductor does have a band gap. And what about insulator?
Huge band gap.
Insulator has a band gap, but it is very, very large. Okay, I can give you some example between insulator and. Can you give an example of an insulator solid?
Backlight.
Backlight.
को लिखा है कि hand writing to confirm we are good for the collateral भी run करना है आप
Yeah, go ahead. Backlight. Backlight is an organic polymer. PVC. Okay. Inorganic solid.
My back.
Inorganic solid. Can you give some example? Come on, you have so many examples. Inorganic. What about diamond? Diamond is an insulator or is
Insulator.
Insulator. It's an insulator. Okay. And what about graphite?
Conductor.
Okay. Okay. Anyway, all of you know about it. But then, if you have a metal, for example, how a band is formed? You look at this diagram. This I took from a textbook. Basically, if you start talking about lithium metal, lithium has 3 electrons, and 1s2, 2s1. So 1s2 we call it as a core electron, and the 2s1 electron is called the valence electron. Now you see that this is kind of a molecular orbital picture. When you go from 2 atoms to form Li2 molecule, you will see that there is the atomic orbitals. They linearly combine to produce molecular orbitals. It is labeled as sigma and sigma star. But when you go to large number of lithium atoms, you will be keep on adding more and more electrons to the bonding orbital and the anti-bonding orbital. When the lithium atoms really become a huge number, let us say Avogadro number of atoms, you are going to have kind of a band. Now the question is, what is the band? The energy levels are so closely spaced. The energy levels are so closely spaced. So instead of calling it as a discrete energy level, you start calling it as a band. You see here, the left side. In left side, you don't call it as a band. In other words, lithium-10 molecule made out of 10 lithium atoms, you don't have a band structure there. You have kind of a discrete energy levels and you are filling the electrons. The moment you go from a small molecule to a solid, we call it as a condensed matter. You are going from molecular level to the bulk. Bulk means you have huge number of atoms. In this case, Avogadro number of atoms. You are going to have so closely spaced levels. So I start giving the name band. Now here, obviously, the band, you see here, it is only half filled because it has a capacity of 2n electrons, but only n electrons are available, so you can fill only half of it. Now the crystalline solid can be regarded as a giant molecule for any theoretical purpose. So how do you construct a molecular orbital? Basically, you will have electronic wave function of atom, and then you will have linear combination. You would have studied somewhere in quantum mechanics. How do you construct molecular orbitals? We will not go into that. The idea is that the atomic orbitals of atoms, they linearly combine to produce crystal orbitals if your molecule is a giant molecule. And the crystal orbitals extend over the entire crystal. And each crystal orbital can hold 2 electrons of opposite spin. So if you take sodium as the example, now you can see that it has 11 electrons. So your valency cell is 3s1. If you are taking Avogadro number of sodium atoms to form sodium crystal, then you are going to call it as crystal orbital, which are combined from atomic orbitals to make crystal orbitals. In other words, 1s atomic orbitals of n isolated sodium atoms will form 1s crystal orbitals. How many? N number. Similarly, you can talk about every orbital. Only thing is, these 3s will be not completely filled, crystal orbitals, because it is only having 1 electron, so you can fill 2 electrons. So only half it will be filled. So that is shown here actually. You are having on the left side free atoms, on the right side you have the solid. When you go from free atoms to the solid, you have the band coming into picture. In the left side you can see that the energy is 1s, 2s, 2p, 3s. I think all of you are familiar with some quantum mechanics, right? How these 1s, 2s, 2p, 3s, all these are coming. Somebody asked you this question, why in 2p orbital there are only 3 orbitals? Why not 5? Why not 4? Can anybody answer? Why there are only 3p orbitals?
Because of degeneration.
Degeneracy means they are of the same energy, but why only there are 3 orbitals? Px, py and pz. I don't have more than 3.
3 axes.
There can be only 3 orientations of these.
3 dimensions.
Okay.
The angular part will become 0 if more than 3 orbitals are there.
It is coming from the quantum mechanics. It is coming from quantum mechanics. For a specific value of L, your angular quantum number, you can have only a specific number of ml. In other words, L equal to 1 actually for p orbital, then your ml values can be only 0 or plus or minus 1. So that is why it is px, py and pz. Anyway, the summary of this slide is, you talk about band when you are talking about a bulk solid. When you are talking about free atoms, you talk about atomic energy levels. 1s, 2s, 2p, 3s. Now what will happen to the energies of these atomic orbitals when you go from free atoms to the bulk? What do you think?
Collapse, different energy bands will mix up and form a new band, like conduction band and
I will repeat the question. I am talking about, for example, 1s orbital in sodium atom energy and the 1s crystal orbital in sodium crystal. Will the energies will be different or energies will be close?
They're different because in bulk there will be interaction with other molecules as well, and
remember, of course I agree there will be interaction, but the interaction will be primarily through the valence electrons, correct? These are all core electrons, 1s, 2s, and 2p. They will not be affected much actually, but the 3s will be affected more because this is actually involved in the bonding. 3s. You can see that in 3s, you can see that, they have written something different. When you come to 1s, 2s, 2p, you can see that they will put a parallel dashed line. Okay, just to indicate that the core level energies do not change much when you go from free atoms to the solid, but the valency orbital energy, the 3s band energy will be different compared to the 3s atomic orbital energy in a free sodium atom. Anyway, now the question is, these energy spacings are so closely spaced, even at room temperature, you can easily excite your electrons from here to here. So what does it mean? I am going to have very good conductivity because the spacing is so close. Now I will ask one question. Is it possible to experimentally observe what is the difference between different energy levels in a band? I will repeat the question. Let us talk about a band. Let us say I am talking about 1s band. Okay. Obviously, 1s band is made out of so closely spaced energy levels. Now, can I experimentally observe what is the energy difference between one level to the next level? Of course, it is so closely spaced, but can I see it experimentally? The answer is, you need to have a very, very highly sensitive technique to really look at that kind of delta E values. Experimentally very difficult to distinguish because it is a band. Now, there are vacant electronic energy levels in sodium crystal that lie at a negligible distance above the highest occupied electronic level. So that means you can easily excite your electrons to higher energy levels when you apply an electric field. So sodium crystal makes an excellent conductor of electricity. Not only sodium crystal, we are talking about metals. Now this picture I am sure you are familiar with. Valency band, conduction band. In a semiconductor you have some kind of band gap. Can I experimentally measure the band gap? The energy difference between the top of the valence band and the bottom of the conduction band.
Yes.
How will I measure it? Your answer is correct, but how will you measure it?
By emitting, by acting on a light of a specific wavelength, like is it conduct or not?
I think it's similar to LED.
Okay. Any other answer?
Sir, calculating breakdown voltage.
Okay. The simplest way to find band gap is to do UV visible spectroscopy. You will find the electronic transition from the valency band to the conduction band. Actually, this will lead to absorption. This absorption can happen in the, for example, UV visible region. Then you can easily do UV visible spectroscopy and find out what is the band gap. Now, if this band gap is very large, obviously it is not a semiconductor. It is going to be an insulator. For example, I can give you another example of an insulator, magnesium oxide. It has a large band gap, for example, of the order of 7 electron volt. So, if it has 7 electron volt, obviously it absorbs some, if you supply that energy, but then it doesn't come into the UV visible regime. It will come somewhere come very, very low wavelength. That means very high energy. I wanted to show this slide just out of curiosity. Look at this slide carefully. The material which is in the colloidal form in all the bottles is cadmium selenide. Okay, let us not worry about what is a nanocrystal. Okay, it is cadmium selenide colloid, and you can see different colors. Remember, chemically it is cadmium selenide only. They are showing different color. This is the photograph people have taken. Now the question is, this is cadmium selenide. Why it is showing different color? There is no impurity. Can anybody guess?
Sir, it
Like
is
it has
pure
different
CDSC.
Concentration.
Okay. Okay, that is a good guess. When you change the concentration, the color is changing, but that is not true. Concentration is same in all the bottles.
The temperature of the liquid is
No, temperature is room temperature.
Band gap is
Sir,
different.
because the air drops are sunlight.
Each one of them has different band gap. That is very, very interesting, correct? And by the way, this cadmium selenide, the particle size is so small. I have written down the numbers here. 2.4 nanometer to 4.4 nanometer. Now the question is, can you call it as a bulk solid? I will repeat the question. Can you call these particles 2.4, 2.5, 4.4 nanometer diameter particles, spherical particles? Can I call it as a bulk solid?
Maybe, sir.
What is bulk solid?
I'm sorry, what?
What is bulk solid?
Very good question. Bulk means we are talking about a solid which has huge number of atoms or huge number of molecules.
Yes, sir. We can say that bulk solid.
Okay, just to hold on, somebody, I am in my office, somebody is trying to call, I will just put up the phone. Just, sorry. Okay, I'm sorry. So, bulk solid means it has large number of atoms or large number of molecules. When you look at the size, okay, yes, Adarsh.
Sir, I think we cannot say it the bulk solid.
It is definitely not a bulk solid because if you take a particle of 2.4 nanometer of cadmium selenide, you can show that it has only few molecules of cadmium selenide. Okay, and it's very interesting. I will not go into much detail of this because this is a little bit out of context, but I wanted to show you that the band gap of a semiconductor, you can vary it. If you can vary the band gap, obviously you are going to modulate the color. Okay, but that will not happen in a bulk solid. What I mean by bulk solid, suppose I take a 1 millimeter size particle of cadmium selenide and then I take another particle which is 10 millimeter size particle. I'm not going to see a big difference in terms of color because the band gap is going to be roughly similar. Okay, this is an interesting aspect. So today, okay, before I go to the, just hold on, let me complete this. I will take up the questions. When you go from atom to a bulk solid, this is how you can show kind of a diagram. If you have an atom, you are having atomic orbitals. If you have a molecule, you are having molecular orbitals. These molecular orbitals can be generated by hybridization or by linear combination of atomic orbitals. From molecule, if you are going to a bulk solid, which has a large number of atoms or molecules, obviously you are going to have kind of a band. We call it as a valence band, conduction band. Usually the valence band is completely filled. The conduction band is empty. And you have an energy gap. This energy gap, of course, depends on the material. Okay. Somewhere between the molecule and the bulk solid, there is something in between which is not in your syllabus, but I can tell you briefly. A quantum dot is actually a semiconductor molecule which is very, very small size. Let us say, whatever previous example I gave you, cadmium selenide, that is also called a quantum dot. It has only few number of cadmium selenide molecules, and you can see that the discreteness of the energy levels is still there. The discreteness of the energy levels almost disappears when you go to a bulk solid, where the energy levels are so closely spaced, you call them as a band. Okay, so I wanted to start X-ray diffraction today, but if you have questions, I can take it up now, and then I will move on to X-ray diffraction.
Sir, I just want to ask, you said that the color difference is due to the band energy gap is different. So, but why the energy is different means there is the same solution or same molecule in each bottle.
Very good. Okay.
So,
How it is done?
Okay. I need to take up something actually. I know you will ask this question, and it's a very interesting question. Material is same. Okay, just 1 minute. Material is same, but then whatever theory you use for the bulk solid, you cannot use it for your quantum dot. In a quantum dot, you have confinement of electrons and holes. For example, if you take a semiconductor like cadmium selenide, it has electrons and holes. I hope all of you are familiar with this. Now, if you have electrons and holes confined in a very, very small space, that leads to something called quantum size effect. Okay, of course, there are theoretical models for this. What is quantum size effect? When you go from bulk to very, very small size, your electrons and holes are confined in so small space, then they start showing quantum effects. A bulk solid may not show that. Okay. For example, if you take cadmium selenide, I was giving you the example. If you have a 1 millimeter size particle of cadmium selenide, you are not going to see any quantum size effect there. But when you talk about 4 nanometer size cadmium selenide, you are going to see quantum size effect. Now the next question, does quantum size effect depends on the size? The answer is yes. Okay, so there is a lot of theory behind it, and if somebody is really interested in, I can, but then maybe it is enough to say this difference you see because of quantum size effect. I think I'll stop here.
Okay, sir.
Any other question?
Sir, one more thing.
Yes, Ruti.
Sir, when you initiate this topic, band energy gap, you asked us one question that in the 1s orbital, the energy is different for free atom and a solid 1s orbital. So what was the reason for that?
Just 1 minute. You are talking about this diagram?
Yes, sir.
Okay. I will repeat what I said. I hope there may be some confusion. You see that 1s, 2s and 2p. They are all called core orbitals. Now on the right side you have the band, 1s band, 2s band and 2p band. Now energy of 1s orbital and the energy of 1s band, they are going to be very, very close because the core shell electrons are not involved in the bonding. They are not involved in the bonding. 2s is not involved in the bonding. 2p is not involved in the bonding. They are all core. The core overlap is not going to be much, but the 3s is going to be involved in the bonding. Obviously, this will be disturbed more compared to the core. I hope it is clear now.
So means there is no energy difference between a free atom and a solid part.
Very, very close for the core orbitals. Very, very close.
And so for valence one, it is slightly different.
Yes, of course.
Okay, sir. Thank you, sir.
Okay. Another I have actually 7 minutes. I think I will start X-ray diffraction. I think we talked about lattice. Crystal structure is periodic arrangement of atoms in a crystal. And the crystal structure can be described by associating with each lattice point a group of atoms. That is what is called the motif or the basis. What is a motif? In each lattice point, you are putting a group of atoms or molecules, for example. Atoms and lattice points are not the same. Remember this. Lattice points are not necessarily physical objects. In other words, lattice points, they are infinitesimally small points in space, and the atoms are physical objects, but the lattice points are not. It is simply array of points in space. I think this I have already explained to you. Now, have you studied a little bit of X-ray diffraction somewhere?
Yes, sir. Modern physics.
Okay. So I am sure you are familiar with this. You use some monochromatic radiation of X-rays. Obviously, monochromatic means you are fixing the wavelength. And the sample, it can be powder or it can be single crystal. Remember, a powder is also called a polycrystalline material. A single crystal is a single crystal. And the X-ray diffraction is based on Bragg's law, n lambda equal to 2d sine theta. All of you are familiar with this. In fact, the father-son duo, actually, W.H. Bragg and W.L. Bragg, they spend their entire life on X-ray diffraction. And that is why this is called Bragg's law. And then what information you get from X-ray diffraction? Just to, again, give you some interest, in X-ray diffraction experiment, you have some source of X-rays. And these X-rays will be falling on your sample. Then they get diffracted and then reaches the detector. Now I will ask you one question here. Scattering and diffraction, are they same?
So can you repeat the question?
Scattering and diffraction, are they same?
No, sir.
What is the difference? Your answer is correct, but what is the difference?
So it depends on the size of the particle. Like if that size is similar to the wavelength of the light, then
yes.
Okay.
Diffraction is like a deviation from the path, and scattering is
Sir, diffraction is always and scattering in waves and particle both.
Okay. Yes, some partially correct, but I want a little better answer.
There can be inelastic scattering also, but diffraction.
Very good. Yes, go ahead.
The scattering can be in all the direction, but diffraction is like fixed in one direction. It will go.
Very close to what I expected answer. You see, diffraction follows some rule actually. X-ray diffraction will happen only when the Bragg's law is satisfied. N lambda equal to 2d sine theta. Scattering can be random. Just it can scatter. Sometimes people call X-ray scattering. Okay, that will be the topic of my next lecture. When light X-ray falls on an array of atoms or molecules, or what will happen to the X-rays, that we will talk about in the next class. But today I just want to tell you, diffraction follows Bragg's law. Scattering will not follow Bragg's law. Okay, it's a very interesting concept. Of course, the scattering of light depends on the particle size, but that is again physics. We will not go into that. Powder X-ray diffraction, I am just showing you some data here, just to show you how it looks like. In the y-axis, you are putting the intensity of the diffracted X-rays, and there is something written here, A dot U dot. This A dot U dot means it is called arbitrary unit. Okay, I will repeat. A dot U dot means it is called arbitrary unit. Now the next question can come. Intensity does not have any unit. How it is possible? What is in the x-axis? It is 2 theta. 2 theta is in the x-axis, where theta is the angle of diffraction actually. And in the y-axis you have intensity. And here I have told you that it is written A dot U dot just to indicate arbitrary unit. Okay. Whenever you are collecting data from X-ray diffraction and try to plot, for example, 3 samples together, and you are displacing the Y scale, for example, here. You are putting one in the bottom, another one upper, another one in the top. Obviously, you are just, change the Y scale. Whatever data you got from the instrument and whatever you have plotted, the pattern remains the same. But then you have displays for clarity. The moment I do that, I put this arbitrary unit. Okay, because this is not the data I received as such from the instrument. I have done something. I have added something to the y-axis just for better clarity. But what is written here, 111, 220, 311, what is mean by this? I'm sure you know. 100, 002, what are they?
Coordinates.
Say it again, please.
Coordinates.
Coordinates. No.
It's just degenerate states, like
degenerate states. No. No. They are called Miller indices.
Sir, maximum intensity is observed.
They are called Miller indices. Okay. You are not studying Miller indices, is it? Is that so?
No, sir, we're not
It was not in the syllabus.
No problem, no problem. Miller indices, probably in the next class, I will show you what is meant by Miller indices. I can briefly tell you. Each plane in a unit cell, suppose I say cubic unit cell, and the cubic unit cell will have many faces. I can represent each face with some number. Okay, that I call it as Miller indices. So when I say 100, it has a particular meaning. Okay, so I will show you in the next class what is. But then I will introduce to you these numbers are actually called Miller indices, and each of these numbers represent a particular plane of the crystal. Okay, you can see that some sample is showing lot of reflections and some samples are showing less number of reflections. That means that these ones in crystallography or X-ray crystal structure we call, for example, this has a cubic structure and this has little more complicated structure. Let us not worry too much about. It is enough to say in X-ray diffraction, you talk about intensity of the X-rays diffracted against the angle of diffraction. And each peak is represented by a particular set of integers. We call it as Miller indices, or we call it as HKL plane we used to call. But then I will show you how a Miller indices is represented in the next class, because I was assuming you know it, but it's okay. I will show it in the next class. I will stop here. If you have any questions, I will take it up.
Sir, can you please go back to the sodium slide?
Yes, Amrit. Yes.
Sir, at Moodle, we are not in any team, sir.
Yes, sir, we got the mail and the platform was Moodle, but we aren't registered there.
No. You are supposed to register. You talk to Professor Anil Kumar. He is the one who handles it.
The course is not there.
Enroll हो गए सबके सब उस कोर्स में से.
There's no one.
Okay, just hold on. You have any questions related to the tomorrow quiz? Related to Moodle, you must contact Professor Anil Kumar and Professor Ramachandran. Okay, because Anil Kumar is the one who handles the Moodle platform, and we are all teachers trying to help. So if you are not registered or you have any problem, you should immediately write to him, or because he is your teacher, obviously, so you can write him.
Okay. Thank you, sir.
Okay. Yes, somebody was asking question related to this. Yes.
How do this oneness ground state relates to this band? Like we studied about conduction band, valence band, but
Okay. You see this valence band and conduction band. Okay. Whatever we are showing here, okay, This is, for example, coming from a group of orbitals, actually, this valency band in that particular semiconductor. This conduction band is coming from some particular group of orbitals, obviously linear combination, okay? And then in a semiconductor, you will have a valency band completely filled and the conduction band empty, and you have some energy gap. Now let us go to the sodium. In sodium, you will find there is no band gap actually, because this 3s band is like half filled, but the next one, which is empty, it is again very closely spaced. So you can say that this part is actually half filled in this case, and then the unfilled one, you can give it a name, actually conduction band, but in a metal, it doesn't have any meaning because there is no band gap. There is no distinction between valency band and conduction band in a metal. You don't have a band gap. Now I will ask you one more question so that that will again develop some interest in you. Gold colloid. Okay. You can prepare in the color of wine red, for example. Gold colloid. All of you know gold is a metal. And the gold colloid is becoming wine red color. Obviously, it is absorbing some light, visible light. Does bulk gold absorb visible light?
No, sir.
No. But then gold colloid is colored, wine red colored. Faraday has prepared 200 years back. Very, very interesting, correct? So, it doesn't have a band gap. So, now what is the origin of the color? Think about it, okay? If you don't find the answer, I will explain, but it is out of context. Like, just I asked a question. Metal.
Cadmium selenide has band gap, you mean?
No, I'm talking about gold.
Yes, but here cadmium selenide is showing color. So, and such question is not asked for it. So, it means it has band gaps in it. Like, we need band gap for color.
Not necessarily. That is what I'm telling. But in a semiconductor, you have a band gap. But that is why I asked this question for gold. Gold doesn't have a band gap, but the gold colloid shows intense color. How do you explain this? That is what I was asking.
Sir, like I too had a question that we read about in metal excess defect, sodium shows yellow color. So how does it shows that without a band gap and like?
No. The color of sodium, that whatever you are selling, that is coming from the defects. Okay, so you would have studied defects in solids, Schottky defects, Frankel defects.
Yes.
That is a very interesting concept. Okay, see, in fact, solid state chemistry, 5 lectures, it is for you, but really, like, there are so many topics one can talk about, and defects in solids is again very, very interesting. Let me give you an example. Zinc oxide. What is the color of zinc oxide?
White.
White. But I can make you zinc oxide which is not white. But it is not, what do you say, I have prepared by a special method. I can show that structurally it is zinc oxide, but it is not having white color. Okay, interesting, correct? So basically you create defects in zinc oxide. Instead of zinc oxide, you make ZN-01 minus X. Instead of simply ZN-O, you make ZN-01 minus X. That will have a different color.
So, sir, a quantum dot crystal, which you referred previously, is actually a semiconductor.
Yes.
So we dope that in the material.
Can you hear me? Hello, students?
Say it again.
Yes, sir, we can.
Great.
Continue, please.
There was another class got over. So let's get started.
Sir?
Yeah, go ahead.
Sir, the X-ray we found in detector does have different wavelength.
Just 1 minute. I am going to that.
One of source.
Oh, okay, very good question. Remember, the detector's job is to capture the diffracted X-rays. Now the question is, whatever wavelength you are putting here and whatever wavelength which are getting diffracted,
We sort
are
of
they
gave
different?
an
The answer is
introduction
no.
last time to sort of give you the scope
Answer is no.
of the physics.
For example, I use copper source for X-rays.
Range of
The wavelength will be 1.54.
So there's a huge range in which the universe operates, and then there is a human scale, which is a tiny window. And so this today, so this is what we have sort of asked. What is the just discuss what is the generic questions in physics in 20th century that has been happened, and then we gave you like a organization of different topics that you are going to learn during your stay here, and we discuss a little bit on the career opportunity. So now we sort of come to the condensed matter physics. So this is a sub part of physics, and this is mainly physics which operates on this human scale of this entire universe. So this is a particular point which focus on this human scale mainly. Then let's understand what is meant. So how many of you have heard this term condensed matter physics?
What's up?
Frequently. Condensed matter physics. So someone said that you have heard it frequently. So can you give me an idea of what you expect?
Maybe we are talking about the highly dense matter.
Correct, highly dense matter. So what is the example of a lowly dense matter?
Air, gas, anything.
Gas.
Gaseous substances.
Correct. And so this is a subject which deals with something which is not gaseous, something which is either liquid or solid. Anything else?
So like crystals.
Yeah, crystal is a solid, right? So to give you an idea, so let me sort of imagine a situation. So imagine that there is some alien, and the alien has come to the earth and meet you. And then the alien is a smart alien, very smart, and as a souvenir for his visit, the alien has gifted you something, some material in a spherical, some sphere, and left. The alien didn't explain you what is this material, what does it do, etc. Nothing. Just gave you and just left. Now the point is that so you don't know what is this material, and so I mean it is nothing familiar. Like it doesn't match with what you know, like familiar with. It's not a metal. It's not a doesn't look like a crystal or something. You don't know what is this. So then probably you take it to some IIT department or something, and then eventually you come to the conclusion that this material does not exist on Earth. It's a completely new material which is not found in the Earth. So then what will be your response to this gift from the alien? What will you do with it?
Study it properly.
Anything else?
Open up that material to find what is it and how it is working inside bulk properties, right?
And what kind of how do you make the study? Like what do you do in the study? So you said open up the material. Anything else that It's
Target density.
EM waves.
Sorry.
We will see the effects with the electromagnetic waves. What type of spectroscopy that matter is giving.
Correct. So you are kind of already so I see that Chirag is already a condensed matter physicist. Anyway, to give you a generic point of view, so there could be, I would say, 3 kinds of broad response to such scenario, depending on the person. First response is that you become afraid because it is something unknown. So you become afraid of it. When people become afraid, they have 2 kinds of response. Either you worship it as a god, and you make a temple, build a temple and put it as an idol and start worshipping the material. The second kind of response is what you see in Hollywood movies. So you become afraid of unknown and you try to destroy it. So you, as they say, you nuke it out. So you try to destroy the material. The third response is basically when we deal with unknown. Is the third response is to get curious about the unknown, and then you try to know or study the material and try to know this what is there, how does it behave, and from that you try to infer what is there. And there is a 4th kind of response. Can anyone guess what is the 4th kind of response?
Temperature dependency.
No, what I had in mind is that you might make a meme out of that material and hope and share it on internet and hope that you become viral. But for yes,
we can establish that material as a brand that is rare, and it might be like artistic galleries and all that.
Correct. So that is also an way. So there's also a response which is like cultural response, that you sort of seek beauty or some art from the material and approach it from so you can, if I generalize it, you can sort of approach it from, you can write a poem out of it, make a song out of it, and so you are kind of approaching it from the art point of view. That's also a valid response. Correct. So all these things are possible. Yes.
So we can sell it.
Yeah, definitely. You can sell it. Definitely. That's another way of approaching it. And most people will try to sell it actually. Right. And then you have to find a buyer, and yeah, but that's perfectly possible. And you see that all of these things are eventually going to become your career or possible career. But out of these different kinds of response, what for our purpose, we will focus on the scientific science part of it. Like we are not going to say study the finance or selling or art or worship or something. So the science part of it. So we'll come to say we will imagine that like a good scientist or good engineer, we are going to study this. So then, as one of Chirag says, that what can you do with it? So what can you do with it? So this is an example. Let's say this is your gift. So it says in this case that kind of questions we study in condensed matter physics. So we are approaching this gift from a condensed matter physics point of view. So first thing it says is cool it down. Now this means, the point here is that most of the things we study in condensed matter, they are in the solid state or in the liquid state in some case. So that means, so this assumes that this gift could be in a gaseous form, and then you have to cool the gas so that it becomes dense. So this is a generic property of anything, that if you cool it, I mean, usually the gas, if you cool it down, it becomes liquid, and then cool it down, it becomes solid. That's more or less the trend. There are counter examples, but the condensed matter phases are usually the low temperature phases of a material. So then basically the point step 2 says practically that you make a solid or liquid out of it, condensed phase, and then you have to measure something. And this is something that Chirag has already mentioned. So you can measure different things. So this is, so I'll come to that. So let's see if I have something more. Okay, here is more. So one thing you can measure is its structure. So basically, when I say structure, I say, like, I mean, you know that. Okay, so let me ask you. So this material is nothing, doesn't exist on Earth, but what about the components? Will it be something made of elements in the periodic table, or it can have? Will it have something that does not exist in the periodic table?
Sir, known elements.
Yes, so it has to, because periodic table is made from first principle. So that means I mean, all the elements that is possible anywhere in the universe according to the known laws of physics are already there in the periodic table. We have counted everyone. So there is not any chance that there is some exotic element, at least from 1 to 92 element number. There is some exotic element which is not present in periodic table but exists in other planets or other part of the universe. So this will be made of elements, will be made of. So then the one question you can ask is that what is the structure? Is it a crystal or is it not a crystal? And there you can do an X-ray, for example, to know the, I mean, so there must be, will it contain atoms and molecules? What do you think? Will this material made of atoms?
Sir, it would be, otherwise I've also heard of neutron stars. So they are not.
But neutron stars don't exist in the, I mean, in the condition of, on the condition that we see on the Earth. I mean, it requires much more, much high pressure, which doesn't exist on Earth. So okay. So why I'm saying condensed matter physics? So I'm sort of imagining that you are doing this experiment in the lab under like room temperature and pressure, ambient pressure conditions, something like that. I mean, condensed matter experiments can also be done at high temperature and high pressure, or low temperature, low pressure, etc. But let's say that we are more or less in the room temperature condition. So I mean, room temperature and pressure, because high and low has some meaning, which you will learn later. What is high and low? Same material can have high and low temperature, can be different for different properties. But it's not a neutron star, that's for sure. So then you can sort of measure its structure. If you do X-ray, you can sort of see how the atoms in the material are arranged. So you can see what kind of crystal it is. What kind of, that is one thing you can do, study. So this is something that you are doing without opening it up, without breaking it. Then you can put it inside an electric field or voltage and measure the current through it. That will give you its resistance, and it will tell you what kind of conductivity. It is a conductor of charge or insulator or semiconductor. You can also do some sort of, I mean, there must be electrons in it, and from these electrons you can calculate the energy levels of electrons, and that will also tell you what kind of the nature of the material, the nature of how this material will behave. So don't worry about these terms. Something that measures the energies of electrons. Then you can also do like how good if you change the temperature. So this is the thermal property that Chirag mentioned, that how much heat it absorbs. So this is one of the fundamental response function for any object or any material, that how much heat it absorbs to increase its temperature by 1 degree Celsius. It's a characteristic property of the substance, so that you can measure, study. And let's say, so maybe I can summarize this, is that so here are some of the it's a one slide summary of the different kinds of study you can do. So you can apply several. So basically what you're trying to do is that you are trying to apply some sort of a forces. These are not only mechanical force, but something that is going to disturb the material. Like it could be an electric field, it could be a magnetic field, it could be light or heat or X-ray, etc. Some radiation. It could be temperature, so you try to heat it or cool it, and see if you heat or cool it, you expect the volume will expand or contract, and you can measure the volume expansion coefficient. So all these things will tell you something, little thing about this material, and you can then compare with what is known to material to us, and that's how you can sort of get familiar with this unknown material. And the third part, so this is the second part of this experiment, is that you are doing this study, but the third part is crucial. The third part says that you observe the response of the material. So response means, suppose you heat the material and you supply certain amount of heat, and the response will be that what will be the change in temperature. And the change in temperature, if you supply same amount of heat energy, then the rise in temperature will be depend on the specific heat of the material. So that will be different for different material. And of course, you can directly apply some force, like as Chirag said, to break it up. So you can apply some force and see how it responds to the force, external mechanical force. I mean, if you apply pressure on it, then its volume will change. If you if you try to deform its shape, then its shape will change, and so on. And so in my research, my lab focuses on basically this kind of external forces, mainly temperature and mechanical force. So I'll come to it a little bit later. In addition, this is about characterizing some particular condensed material. But in addition, so this is one aspect of condensed matter physics, characterizing the material. The other aspect is that to understand why a material is solid or a liquid, why it is not a gas. What is this condensed phase? How does it? So what is the phase of the material? Now here I will give you some example. Meaning basically you can see that these materials are made of some building blocks, which could be atoms or it could be molecules, and these atoms and molecules come together in a very dense packing, and that forms some structure, and this packing has certain behavior, which is characterized by all these studies. And then overall you will see that, let's say, take the case of water. So water is under some temperature, it will become it is liquid, and then if you decrease the temperature, it becomes solid. So this is a Niagara Falls, which is frozen in winter. So that means as you change temperature or as you cool, then there is a drastic change in the behavior of the water. Same material, different behavior under different temperature. And this is called a phase transition. So we say that in this particular temperature condition, the water is in the liquid phase, and when you cool and the temperature is below 0 degree Celsius, it is in the ice or solid phase. To identify all these different phases is another goal. This is also something we study, because this is how we try to organize or classify different condensed matter under you can label them under different phases. So okay, so now here is the slide for the significance or why study condensed matter physics. I mean, of course, you will have no choice because it is part of your syllabus, and I think it's a core course for both engineering physics and BSMS. BSMS definitely, engineering physics probably also. So you don't have any choice. But suppose if you had a choice, if it were an optional course for you, so what is the significance of studying condensed matter physics? So I'll give you two examples. The first example is that, so this is a very, like, all the new technologies come almost all of them comes from this area. And this is the example that, so this is a diode. So initially, people made vacuum diode. So it's a cathode and a diode means di means two, though, it is di, and ode comes from electrode. So it is two electrode, cathode and anode. Then people discovered a completely different technology, which is called PN junction semiconductor. And the advantage is that this vacuum diode, if you come to the physics department lab, you will see some experiments, first year experiments has vacuum diode. So one diode will be some 1 feet long. Whereas you know that there are millions of such diodes in your mobile phone. So when you change the technology, they become much smaller. And which, when you scale it up, it becomes an IC chip. And that application comes to the computer. So everything, all of these things comes from condensed matter physics. The other part is that this something specific to 21st century. So 21st century has its own challenges. The biggest challenges are something like climate change and air pollution, global warming, etc. And there are a lot of questions that are unknown. And for example, to understand climate and global warming, etc., one of the very basic, so this is something Professor Roddam Narasimhan told me. So he is a very great geologist, not geologist, fluid dynamics engineer. So he told me that a very basic question is that about climate is how clouds form. So clouds form, meaning that the water vapor has to sort of come together and become slightly more dense, and which we see as cloud. And then those clouds, when they become more denser, then they become rain. But then this process is a subject. I mean, so this is kind of looking at phase transition. So this is what comes under condensed matter physics. And this process, no one knows the answer, he told me. Another challenge is, for example, biological physics. So I will try to say more about it. But to give you one example, quick example, that let's say all of you have heard about coronavirus, right? So this is a virus, and so one of the important question is that how does this virus move in air, for example, or how does this virus, what are the properties of this virus, and when it falls on a solid surface, what happens, and all these things. So many of these questions, the virus, the phase of the virus can be studied using from a condensed matter point of view. So I'll come to this in a bit more detail. But there is one fun. These are all what you say the applied part. But there is a very fundamental motivation, which is that to study complex system. So I will give you a simple definition of what is a complex system in the next slide. But this is of course a system which is kind of large human scale system made of many atoms and have some complicated set of behavior. Now here there is a very interesting phenomenon which is called emergence. So here is an example. Suppose you start with the idea of a point. So this is a zero-dimensional concept. And now when many points come together, they build a line. So here is a line. And now when you go from point to line, you have a new property which is the length of the line. So each of the individual point did not have this property. A point doesn't have a length, ideal point. But when they come together and make this particular object, which is a line, there is a new property that we call emerges. And similarly, with the line, if you can make objects made of this line, which becomes a rectangle, and this rectangle has a new property which is the area. So am I able to explain this example?
Yes, sir.
So the point is that the idea is that if you take simple building blocks and using simpler object, you can make more complex object, and this more complex object has some new properties that is not present in the simpler object. So this phenomenon is called emergence. So this was beautifully explained by a very famous condensed matter physicist, Philip Anderson. So he had a very famous article which is called "More is Different." So maybe let me show you this article. This is a very famous 4-page article. So I have put the link. So if you are interested, take a look at it. It's a very provocative, very interesting article, and it's become very famous. It's called. So the idea is that more is different, and so when you have these complex of objects, most of them are what we call disordered, meaning they are not crystalline. So then the challenge is that how to predict, how to understand this emergence and how to. So this is a new frontier of our human knowledge. We don't know how to. We don't know what kind of properties will emerge as you go from a simpler object to a more complex object. But this is the challenge to understand that. So let me give you a very simple way to define what is a complex behavior or complex system or complex object. So here is a chart. So I'm not going into the chart, but just to point out is a 2D map of different topics that covers a broad range of syllabus in physics and engineering, some of which may be familiar to you, like RC circuit, radioactive decay, a lot of physical phenomena, oscillator, mass, spring, etc. Some of the thing may not be familiar for you, familiar with you, and some of these you will be studying maybe in your course. So the idea is that we have arranged this using two variables, two axes. The first axis is the number of variables required to describe that process. So as you increase the number of variables, then it becomes more complex. Now there is a catch here. So when you go to n tending to infinity, it becomes a continuum system. Like there is no number, you cannot count, no longer can count the number of variables. Then again it becomes slightly simpler, just because you can describe in terms of waves, and waves are effectively the number of variables become less. So this is the part which is the more complex or more difficult. And the other axis is the non-linearity, which means the underlying equations are the linear equations that describe the process or non-linear equation. So non-linear equations are much harder to solve, and the solutions of those equations are more complicated. So take a look at this map, but I'm not going into details of this. So now I just wanted to say this, that this year, that is 2021, the Nobel Prize in Physics was awarded for research on complex systems and disorder. So three guys, probably you know there was an institute lecture on covering this year's Nobel Prize. So three guys, two of them worked on climate research, which is the Earth's weather is a complex system. It has a huge number of variables and non-linear. It's a complex system. So they studied that particular system. And the other person is Giorgio Parisi. So he studied some materials which are called disordered. So it says that around 1980, Giorgio Parisi discovered hidden patterns in disordered complex materials. His discoveries are among the most important contributions to the theory of complex systems. They make it possible to understand and describe many different and apparently entire random materials and phenomena, not only in physics but also in other very different areas such as mathematics, biology, neuroscience, and machine learning. So this is an example of the scope effect of influence of condensed matter physics to other areas. So this is the citation quote from the Nobel citation. So let me tell you a little bit more about what is disorder. But before that, so now I'm going from condensed matter physics to some more specialized topics, some subtopic of condensed matter physics. So I'm going to divide it into two parts. One is called hard and is called soft. So this hard and soft is not like how difficult or how easy it's. It is that if you apply force, how does the material respond? If it is very hard to sort of deform, it's called hard. So these are essentially crystals which are made of periodic structures. Here are some example pictures. And this is what you essentially study, you are going to study in your traditional condensed matter course, mostly based on these crystals. So you are going to study crystalline solids. And so these are the different properties that are part of your syllabus. The other part, which is not so covered so much in the traditional course, is the soft condensed matter physics. So the point is that most of the material that we see around us, they are not made of regular crystalline periodic structure. And this is what I mean by disorder. So order means crystalline structure, disorder means non-crystalline structure. And here are some examples. So first example is this screen of this phone. It is made of glass. And so each of the example, so it shows the object at two different scales. First in the human scale, which is what we say with our naked eye. And the second is the under microscope, the atomic building blocks. If you look at the material under a microscope, high resolution microscope, and can actually see the individual building blocks, then how will they look like? So this is the resolution of a nanometer, 4 nanometer. And the second example is toothpaste. Third example is, I think it's a mayonnaise. Fourth example is a foam. It's a coffee foam. Fifth example is sand particles or grains. So all these materials are all around us, and they so when these building blocks come together, they are called soft because it is easy to break them apart. So the cohesive bond between the building blocks are very small compared to the crystalline structures. That is why they are called soft, and they can vary, as you see from these pictures. The building blocks can vary over an enormous size. So they can vary from nanometer scale to millimeter scale. So you can in some material you can observe them directly, and some material you cannot. And some examples are the like polymers and DNA and rubber and colloids, etc. And here, this one of the biggest question is, are these materials solid or liquid? That itself is a very complicated, because a traditional way of describing them as solid or liquid does not work very well here. To give you an example, suppose if I give you butter, what is this? Butter is a solid or a liquid?
It is a colloid.
Right, but will you say butter is a solid or butter is a liquid?
So it depends on temperature.
Yeah, so you take it out and put it on the table, then what is this?
Liquid.
Solid. Or solid. You can still cut it with knife. Can you cut a liquid? How about curd or ice cream?
Yes, so that we can cut.
But it can also flow, right?
Yes, sir.
I'll give you a somewhat more let me make you more confused. What is toothpaste? It is a solid or a liquid? So toothpaste has this property that if you put it inside, as long as you are not putting any force, it stays inside the tube. If you put the force from outside, it starts to flow. So how do you characterize it? Solid or liquid?
Sir, more towards solid because it is easy to move, not really easy to flow.
But it doesn't have any particular shape. It takes the shape of the tube.
Yes, sir.
So does it satisfy the criteria for being solid?
It satisfies most of the criterias.
Like what? What makes a solid a solid?
So the bonding between the atoms is good enough to not allow any random flow of the material.
What is a random flow? So mixture of cornstarch and water can take impacts like solid. Yeah, that's also another famous example. So let me read it out. So Arav has put it that can impact mixture of cornstarch and water. It can take impacts like solid when hit and can flow when kept free. Right. So this is another example. So you can go to YouTube and see some beautiful videos. So these are examples of, meaning when you say random flow, then you have to define random in some way. And you will soon find, if you think about it, that defining it, the random is not very easy. Like how much pressure you give, then it will start, I mean, you will consider it to be solid. I mean, even if you give mild pressure, then liquid, I mean, paste may not come out of the tube. Okay, so Araf says these are called non-Newtonian fluid. Okay, good that you mentioned, because I'm coming to this. Then there are other things like these living cells. This is okay. So this is another important part. So okay, so let me show you this thing. So this is also a subject. So what I show you on the top is a collection of bacteria. Here is a collection of birds. This is a collection of fish. And at the bottom you have these are a collection of robots, nano robots, some grains vibrating, some light activated colloid particles. So these are all looks, they are not regular periodic structure, so they are disordered and of course complex. And these systems are called active matter system because the particles in each of the individual particles can move, like they are self-propelled. They have a mechanism for motion by themselves. And the idea is that like 10-15 years back there was a like debate in the field that whether you can ever describe the life or living systems as a physical system. Like we study, let's say when you do mechanics, we study, let's say, throwing a projectile. But isn't it much more interesting to sort of consider the motion of living beings, but which we never actually consider in science or engineering curriculum. So instead of throwing a projectile, it is, I would say it's much more interesting to consider the motion of a jumping frog. Unfortunately, it's not part of the curriculum, but even there is an even more deeper question, which is that the process, different living process like birth, death, the growth, all these things, can you study or describe using the concept of condensed matter physics or physics? So this is an emerging area which to study the physics of life. So it's an emerging frontier area, and it's a because living systems are soft, so they are part of what is called the soft condensed matter physics. Now let me quickly go to you one thing. So it's because I have put this non-Newtonian and Newtonian thing. So okay, so here is one thing that how whether something is, so there are, so here is an example of some material which is in a gray area between solid and liquid. So this is an experiment that is going on in University of Queensland. So a very simple experiment, tabletop experiment. So there is a funnel in which there is some lump of tar or pitch, and they are observing that the drop of the pitch drop in this bucket. And this process is so slow that there are only 9 drops in 90 years so far. And this experiment is actually live, so you can go to YouTube and you can actually take part and to observe this experiment. So this is called 10th drop or something. But anyway, so let me go to a little bit more details about how to understand this. So what we study in, so we said, what I told you is that there are certain set of materials which are soft. Give you some examples. Now we come to what we study. So one of the question that I focuses on is to study the mechanical response, which means that if you apply some force, then how does it volume and shape deforms. In order to understand that, you have to understand few things, which are what are the different kinds of forces that when I say forces, which means interatomic forces, intermolecular forces present in different kinds of material. So here I give you several different types of examples, but I'm just mentioning the names so that this is van der Waals force, and this is a generic picture of how does it look like. And the main features is too that at short range, when so this R represents the distance between two atoms. So at short range, this is a repulsive and very high. The force is very high. So the slope. This is the potential energy. So that means the slope will give you the force. And as you see, the slope is very steep. That means the slope is very high, and this direction is in this direction. That means it is a repulsive force. So when you put two atoms come close together, they will repel each other with very large magnitude. And when you go when you go to a large separation between them, then this force becomes attractive. So the slope, if you calculate the sign of the slope, the sign is opposite in this regime and in this regime. So this is the feature of van der Waals force. Then there are other forces, because the particle there are charged particles, the ions inside the material. It could be ionic interactions, and there are several others. So instead of giving you one sentence introduction, what I'll give you is some brief reading material to know a little bit more about them. With the focus should be on not going into the details, but to know about the magnitude of this force and which materials they are present. Okay, so now to address this question, so the question I said is that, so we study, so let's say we have dense solid, liquid, and something in between gray area, and these materials are soft, they are easy to deform. Then how to describe them? So one specific question is that how will they respond to external forces? And okay, so one thing I forgot to mention is that one of the question here about this kind of material is a very simple question. Can we call them solid or can we call them liquid? And if when they're behaving as solid, why are they behaving as solid? So this is the simple question, the simple research question that I am kind of focuses on. Now here, so we have two different models. So these are like ideal extreme behaviors. One case, you can imagine that this material behaves as if the atoms are connected by springs, and they produce a pure elastic response, pure spring-like response, which is called a Hookean solid. Hookean comes from Hooke's law. So this is a solid which follows Hooke's law, which basically means that if you apply some, so instead of force, we are talking about stress, which is force per unit area. And this is a particular type of force which are called shear. So this is an example here. So this is how we are applying the force. So we are trying to deform the shape of the object. So this is the effect. This is called shear force. Then the shear stress or shear force per unit area, and the deformation is measured as let's say the angle. So this angle measures the deformation from its original position, and this angle is called shear strain. So the shear strain is proportional to shear force, shear stress. So this is the particular law that defines the Hookean solid. And why we put this kind of flow? Because if you take a liquid, it cannot, which the defining property of a liquid is that if you apply shear stress, it will start to flow. So by applying this kind of force, you can distinguish between what the liquid-like behavior and solid-like behavior. And then this liquid will start to flow, and then the flow rate can be described by strain rate. So here the shear stress per unit area is proportional to the strain rate. So here is the same thing in terms of mathematical equation. So sigma is the shear stress, and E is the shear strain, and G is a constant, is called the elastic constant, or is called shear modulus. So it's basically the Hooke's law that force is equal to K times deformation of the spring. So this E is as if like a deformation of the spring, sigma is like force, and G is like spring constant. So this is the Hookean solid, or it is called a perfectly elastic response. The other extreme ideal model is that perfectly viscous response. That means this shear force. So here what is dominating is the viscosity of the fluid, and if the material, the fluid has a velocity v and starts to flow with a velocity v, and let's say here it is at rest, and there is a change, the velocity gradient v by y, and a, so f by a is the shear stress. So then the shear stress is proportional to the strain, the velocity gradient, which is called the Newton's law of viscosity. So this is called a perfectly viscous response. And the materials around us, what you see, these toothpaste or colloids, etc., they in real life, they show a mixture of these two limiting behavior. And this is called a viscoelastic response. That means you need to describe, you need to know the both the viscosity as well as the elastic modulus for the material. So they are not fully solid, they are not perfect solid, they are not perfect liquid, they are in between. Okay, so maybe, so okay, so I don't want to say more, and I think I have also run out of time. So instead of, so what I will do is that I will give you a brief few pages of reading material which you can study, which you should study, so sort of to know more about like what is the what kind of forces are there in the in a soft soft material, and what are these limiting ideal behavior response to external shear stress, and yeah, that's it. So I will stop here. So if you have any question, then you may ask.
Sir, I have one question to ask.
Dave.
Sir, I only wanted to know, sir, what is the level of mathematics needed for this course as compared to other highly mathematical courses like string theory or astrophysics or anything like that?
Which course?
This condensed matter physics.
Oh, you not level of mathematics is see there are okay. So when you study what the condensed matter physics you study in your that you are going to study in your curriculum in second or third year or fourth year, that level of mathematics is less compared to string theory or particle high energy physics theories, etc. Because what will involve it will involve solving partial differential equation and knowing complex numbers, algebra of complex number, and calculus of complex number, like doing and it will involve, so you need to know integration and differentiation and solving differential equation. That is that's all.
And sir, as a whole time dedicated field of condensed matter physics is there. So sir,
full time dedicated field?
Sir, as in beyond graduate level, like the people who are definitely studying condensed matter physics for their entire life and doing a great deal of research in that field. So are they using such mathematics daily, or like what is the mathematical scenario there?
It depends. So for example, people who do research, now there are three approaches to research. First approach is doing experiment, like measuring something, measuring electric field, measuring the response, measuring the conductivity, etc. So those who focuses on experiment, they actually don't focuses on mathematics so much. They just do experiments. and they focuses on experimental methods more, and the accuracy of the experiment, resolution of the experiment, etc. Second thing is that analytical modeling or theory. So in analytical modeling means doing paper pen based calculation. Like this is an example that I give you, that is sigma equal to G by E, etc. Right, coming up with equations describing the system. So they uses more mathematics, and but then these equations are mostly differential equations, solving the differential equations. And the third thing is that some people do computer simulation. So they are kind of, you can think of it as a mixture of both. So they do a lot of coding. So again, they don't use the math so much. So yeah, so there are all sorts of diverse range of use of math. Now, one thing I should mention is that so the string theory or high energy physics is complicated. Mostly only thing that makes them mathematically complicated is what is called field theory. So they are also doing differential equation and integration and differentiation, but they are doing it using on fields, and that is what makes it complicated. So it's a slightly more abstract, but those techniques, so there are people who sort of, like these days there are high energy physicists who applies those mathematical techniques to solve condensed matter physics problems. So those are also applied in condensed matter. Good question. Anything else?
No, sir. Thank you, sir.
Welcome. So any other question? Okay, so let us stop here, and good luck for your exam.
Thanks a lot, sir. Thank you, sir.
Yeah, so for the exam purpose, actually I will give you a few pages of reading material, so go through it. It will be useful for your exam purpose.
Really grateful, sir.
Okay.
Thank you. Thank you, sir.